So in between that, I started working on the
Looks like this is not a full ride.
What? I was a service.
We've been losing people consistently.
The labs? What? The labs?
Yeah.
Did that for 5 years and then it was like, screw that. Toxic place to be. Like construction.
Another question I have is,
Super
fall break is next week, and it starts on Thursday.
Very
You got that
similar.
class on that day?
Yeah,
I don't know, you
so
can ask him.
5 years of that was
Yeah.
enough.
Okay.
I like computers.
Definitely shouldn't, I don't think we will.
Love computers.
You want us to turn the lab in today, or is it?
Yeah,
you want-
exactly.
yeah.
Hawaii.
You don't have
You
to.
can
Work
definitely keep it.
remotely?
Yeah, we can turn it down. Not even possible. It's like almost. Are you done?
Yeah, I'm done with
Yeah,
that.
just bring it.
Okay. I'm okay with that. Spend time with my wife while I work.
All right, shall we get started?
How many people in this class?
We started with like 3.
Like
NBC was almost full.
Yeah, it's like losing
Physics physics is like pure repellent.
I don't think it's physics.
It repels people.
I think that's definitely more like
I don't think
I
it's,
think it's
physics. What?
I agree with that.
Look, I'm not here for the smart, or because I don't believe somebody's smarter than anybody else. I just think that if you're smart, you can stay at home with your mom and be smart, you know, you don't need to be here.
Right to repeat your
We're here to learn. And pretty much if you're curious, that's all you need, just a passion, right? And just keep working hard. Don't compare yourself to anybody. Don't think somebody's smart and somebody's dumb. It's just, everybody's dumb. You just.
The fact that all of the assignments in this class are.
The half-empty part of that. So yeah, you just have a passion. You know that you're here because you want to know how things work, right? Am I right?
Something like that.
Yeah. If you're not, then just try to pass and get out of here. But if you don't know how things work, then listen and just enjoy it. Yeah. Right. We're talking about chapter 8 today. It has 6 points we're going to talk about. Momentum and impulse. Those are like two faces of the same coin. Very similar to each other. And then we're going to talk about conservation of momentum, why momentum is conserved. That's a very common question. I'm not going to answer that, but we're going to talk about what happens now. Momentum is conserved. If you hit 2 marbles, they bounce. So momentum before hitting is the same like momentum after hitting. So we're going to talk about that and explore it mathematically. Then we're going to talk about conservation of momentum. It's a relation to collisions, which is just more math. If a collision happened, is that collision elastic or inelastic? Is it 2 marbles or is the bullet in your chest? These both are collisions, but the results are different. You get a bullet and you just bounce back, but 2 marbles, both of them bounce. If I shoot this guy, you didn't know you were coming for a stand-up comedy. So if you shoot somebody, it's not like the bullet bounces off of them like an Iron Man. So that's an inelastic collision because both of them bounce together. They just move together. But if you have 2 billiard balls bounce off of each other, that's an elastic collision. So we have 2 types of collisions. We're going to explore both types here, and then we're going to concentrate more on the elastic part, right? And then we're going to go to COM, center of mass. Center of mass. Everything has a center of mass, right? That's why you can't carry your girlfriend like in the movies. Most of her mass is like in different places, and it's really hard. In the movies they show it like she's a freaking sphere, but it's not true. And then we're going to talk about the rocket propulsion equation. All of this, we know that things have a mass, right? And the mass is fixed. You have a mass, you're not losing your mass. What if your mass becomes smaller in the middle of the motion? That's a whole different story. And that's how rockets work, right? So let's get started here. Do you guys have any thoughts?
I have a question.
Yeah, go for it.
What's the difference between center of mass and center of gravity?
Good question. Center of gravity, what do you think center of gravity is?
think that's where gravity pulls you, like you average all of it out.
Yeah,
There would be a
so
point where it pulls you.
I've been doing this for a while and I haven't heard of center of gravity, but it's a different word of center of mass.
Oh, it's just the same.
Pretty much, yeah. And if you have a big mass, like really fat, you can attract people, right? Like planet Earth or the sun. All right.
So they're the same thing.
Yeah. So. Let's talk about momentum. Does anybody know what momentum equals to?
Yeah, it's like mass times velocity, right?
Yeah. He was a smart guy in the class. Thank you. I'm joking. All right. So we all know that momentum is that, right? But what does this describe exactly? It tells us that if you move a mass with a certain velocity, we call that momentum. There's nothing to it, it's just who knows the Newton's second law?
Force equals mass times
Yeah,
acceleration.
exactly. F, and I put this line above it because it has a direction. If it doesn't have a, if it has a direction and you write it as a scalar, I can't accept that. That's like cursing at me. So please don't do it.
You're different.
If you're a scalar, you're a scalar. If you're a vector, you're a vector. Easy, right?
Okay.
We know that force equals ma. How do you describe this in words? How do you describe it in words?
The amount of force is equal to the mass times the acceleration.
Yeah.
So the more acceleration, the bigger it is, the more force it has.
If you have two apples and you distribute them on 3 people, means each person takes 2 apples, right? This person takes 2 apples, this 2 apples, this 2 apples, 3 people, end up with 6, right? That's correct? Let's use this analogy here. You distribute the mass on the acceleration. So it's similar. The mass is accelerating. If you have a mass, but this mass is accelerating, then that's a force.
Okay.
Yeah, if I kick you down the stairs. All right. Well, this does not really describe the force. That's just mathematical. We want to know better. And the better way to describe force is it's the first derivative of momentum.
Is it though?
Oh yeah. Yeah.
I guess the derivative of scalar and no, it's constant. If your mass is maintaining, it's constant.
Yeah. Think of it. First derivative of velocity is acceleration and then multiply by mass and get force.
And so, okay.
That's mathematical, but we're doing physics, we're not doing math here. So the physics of it is that incremental change in momentum, that's what force is. Now we know what momentum is. What if you're changing this momentum?
Well, then either your mass or your.
That you call that force. Exactly. It's a smart guy in the class.
I'll wait till it just
All right. Does anybody know what kinetic energy is?
Yes. It's the energy of motion. The thing with the.
All right. We know that energy equals K plus P. That's a big P. Momentum is a small p, by the way. Just lingo. Anyway. Well, which means if you're on top of a building, you're gonna jump, right? You have maximum potential, right? Plus 0 kinetic, and that's your full energy. But if you're in the middle, then your energy is the same, it doesn't change. It's always constant, the same. And just the ratios of, yeah, exactly. So you will have potential plus kinetic, and they're possibly equal to each other. And if you're at the bottom, not on the floor, you're almost gonna splash on the floor. Almost. Splash, you made of 80% liquid. So almost a splash. So
You
you're,
have negligible,
there is no potential anymore. You're in the bottom, but you have K max. Yeah. So this is just a quick description of what kinetic energy is. And we know that kinetic energy equals half mv squared, right? Well, if we look at potential, and then we look at kinetic energy, we're kind of similar, no? We're kind of similar. But let's talk about that. Can you say that potential is proportional to velocity?
Potential energy? Or just
Sorry, momentum. Sorry.
Momentum is proportional to velocity, but it looks like kinetic energy is the integral of momentum. Oh.
So, kinetic energy, which is not a vector, it's a big K, proportional to v squared.
Yeah.
Everything else is just a constant. The mass, half, whatever. So there is some relation between potential and kinetic energy. Of course, this is also a scalar. That's how you make it a scalar. If you have a vector, it could never be just a v anymore. Impossible. If you want to make it just a v, you just put two lines here. Now that's kind of equivalent to writing v, but I don't like writing v like that. Because once you're a vector, there is no way back. There's no way to just be written anyway. This is a scalar, K, kinetic energy, so we just write it as a scalar like this. This is also a scalar, same thing. I just don't like to write it V like this. You write what you want, I'm just showing you the proper way of what I mean. Now, mathematically, we understand this is a mathematical explanation. That potential is proportional to the velocity. Momentum and momentum, the magnitude of momentum is proportional to the magnitude of your velocity, even though they are both vector. But kinetic energy is proportional to the square of the magnitude of the velocity. Right? That's a mathematical explanation, and the mathematical explanation is the easiest because you can see it in the equations, right? This equation, this equation. What about the physical explanation? It's not too bad.
Like,
So,
the more speed you have,
if you, yeah.
so get the more speed you have, the more momentum you have. That makes sense. I don't understand why.
All right. Well, let's talk about it physically, and that will give you an intuition why. To be able to describe the relationship between momentum and kinetic energy, we need to talk about something called impulse. And we call impulse, let's talk about impulse. We know it as J, and it's, of course it's a vector. Right? Yeah. Now what's impulse?
I've never heard the word before. Except for in Star Trek, of course.
Yeah. So impulse is pretty much F delta T. A change in time while applying a force. If you're applying a force on something, there's a time difference from when you start to when you're done. Yeah.
Multiplied by delta T?
Yes. And that we call that impulse. Think of it that way. You're applying force on a body at small increments of time between period T1 and T2. And during that motion, while you're applying the force, that's what you call impulse. If you add all these little forces along the time axis, from time 1 to time 2, from 1 second to 2 seconds, You're applying a force on the body. The impulse is adding the force across all that time. So if you're applying 5 newtons on a body for 10 seconds, what's the impulse?
50 something.
Yeah. 50 what?
I have no idea what the unit impulse is.
Of course, to write it in a better way, we're summing up pretty much.
I mean, Newton seconds.
Yeah, that's what I would think is Newton second.
Newton seconds, exactly. What's a Newton second?
1 Newton. Oh.
Kg per minute.
Right? Hey, what is this? Right?
Okay, well, okay.
So impulse is kind of like momentum, if you think about it.
But it is a kilogram. It's a.
Kilogram per meter kilogram meter per second square multiplied by second gives us kilogram meter per second. So impulse is summing up all the little force elements that you apply on a body during a time interval. That's what you call impulse. It's like a pulse, like a heartbeat where you just send a pulse. Now there's two types of forces. There's a constant force and there's a changing force. Right? Let's talk about the constant force. If you're applying force on a body consistently, then the summation of all that force you're applying equals delta P over delta T. Changing your momentum will change the time. See, this is exactly similar to that, but this is a more general picture. Because this D is tiny, like infinitesimally small increments. But this delta, it just means from the start to the end. It's a constant force. So what would J be in this case? Do you agree that J, the impulse, equals delta P?
Yes.
P2 minus P1.
That's no sir.
Make sense?
Yes.
Yeah. And that's called, actually, that's a theory. That's a theorem, impulse momentum theorem. This theorem gives us something so fundamental about the universe that a change in momentum is impulse. Now, a change in something is kind of similar to the thing. For instance, a change in force is kind of similar to force, right? You're just changing it. You're not. So it's the same dimensions, right? 5 meters minus 2 meters equals 3 meters. What if I have only 1 meter? Well, both of them have the same dimension. It's just one of them is a change and the other one is just is. So that's kind of the same thing. That's how you describe impulse. It's a change in momentum. Yeah.
But that's only for constant, right?
For constant force, if you're applying a constant force on the body, then your impulse is just a change in momentum. It's kind of shortcut. You're not going to go through tiny increments of forces anymore. You just have a constant force. So you kind of just ignore the force and go immediately to momentum. And from that, you can describe the impulse as a change in momentum. This is a general picture. All right. As it says here, impulse of the net force that acts on the particle during delta t. That's equivalent to the change of momentum of the particle during that interval of time. That's what I'm saying. Now let's talk about non-constant. What if you're applying changing what do you do? In this case,
Integrate
you
force.
sum the force. Yeah, you integrate it. Exactly, because it's non-constant. If it's non-constant force, then what do? You have like force 5 and then 7 and then 2 and then 4 and then 1. Different types of forces. Like lifting something, lifting weights. You're using different increments of force. You're not using constant force. You might think you are like the Hulk, but you're not. You know, when it's lower, it's a little easier, and then when you carry it for a little bit, it gets harder and harder. Especially if you're doing CrossFit, it's just lots of increments, lots of different types of forces you're applying right now. It's not just one force, right? So in this case, integrate. We all understand the meaning of integration. Integrate. Differentiate is different from each other and pick one of them. Integrate is to just get all the tiny things and put them together. That's integration. So you integrate. What are the limits of the integration, the boundaries? When you integrate, you integrate over time. You're applying these tiny forces over time. So you integrate from your start to the final time. So of course it's dt is the element of integration. And what would that equal to? We can just use these equations.
Well, that's already force over time, so then that is Newton seconds, which is force.
You guys agree that this is correct? Think about this one. Where does that come from?
Well, like, that's, then you could just say that because of the, what is it? The fundamental theorem of calculus, that just,
Yeah, so now you have this dt here,
whatever
it
cancels.
just goes here. And the force is equal to dp over dt. Force equal dp over dt, right? There's many ways to write differentiation. This is my favorite way of writing it. But you can write it in many ways to differentiate. This is basic stuff, but let's mention it quick. If you're differentiating d pi dx of y, that's equivalent to dy dx of y. That's equivalent to dy multiplied by 1 over dx. This is just language. It's just lingo. But the thing is, this is not really a quantity. It's not like 3 over 5. It's not like that. They're kind of attached to each other. But we treat it this way, like normal numbers, until we can't. But yeah, in this course, it doesn't matter. It's okay to move it, just move it around. If we move it around, we see that dt cancel with dt. Right? Now you're independent of time. Time doesn't matter anymore in this case. If you're, again, we're talking about integrating all these tiny different amounts of force you're applying on an object over time. When we integrate this, we end up with something like this. This eventually ends up to be like this, right? That makes sense? It's an integration over momentum now. Completely. And if you integrate that, what do you get?
Just your momentum, just vector p.
Do you agree that it's just P2 minus P1? Because if you integrate this, you get P, right? And that P goes from P to P1 to P2. And that equals, just put the P2 in there. So P2 minus, put the P1 in P1. So you get that. Just normal integration. Oh, what is this? Okay. That's that. That is impulse. Right? Even for a non-constant force, you can still generally tell that difference in momentum is the impulse. Now we proved it twice using constant force and non-constant force. Right? Okay, so we're able now to define impulse if your force is constant by this formula. That's, we use this formula to tell that delta P equals J. Or if your force is not constant, what you do, you integrate. And you can use this formula to tell that delta Q equal J. Alright. And this is the first part. Let's, alright. Guys ready for me to raise?
Yeah, let's make our comments.
By the way, a little side note. There's something called work energy theorem. We just talked about momentum impulse theorem.
Yeah.
It's a relation between momentum and impulse, where
Work energy
your
is the same
momentum,
thing.
the difference in momentum equals your impulse, right? That's a theorem. This is another theorem in our course that says what? That work is pretty much the difference in your kinetic energy. That's the work you do.
Okay.
Now we know what work is. If you're applying energy in a body, you're applying a force. Eventually that force is just represented as energy. And that energy changes, right, from the beginning to the end. Then all of that energy applied, we can just call it work. And of course this stuff is measured in joules. And you can see symmetry. Physics is about symmetry, you know? Stuff that looks like each other. Symmetry, what is symmetry? Simply, symmetry is how can you say that? It's I'm looking for the right words to use for that. And symmetry is when you apply something on a body. Say you have a sphere, right? This is a sphere. And you're a marble. And you're rotating it. What happens? Any transformation you apply on it, it stays the same. We call it invariant in particle physics. Just the word invariant means it doesn't change regardless of the transformation you apply. So if you rotate a marble, it's still the same. What if you have that's called rotational symmetry. What about a rope? If you move the rope forward, it's still symmetric, it still looks the same. That's called translational symmetry. So, just a little side note what symmetry means. This stuff was discovered by a lady, her name is Emily Noser. I had a crush on her for a while. All right. The second thing we're going to talk about today is conservation of momentum. Don't read that long, please. All right. To really talk about conservation of momentum, let's talk about forces first, because we all understand that. Again, force equals what? Differentiation of momentum, right? So let's talk about forces to understand. And there's two types of forces in a system. There's F internal and F external. If you want to abbreviate this, the word external should be ESD. Don't just write ES. Alright, so F internal and F external. Simply, F internal is the force that particles within a system exert on one another. Right? Like the molecules in your body. They're fighting, they're doing whatever they want to do. All of these forces are internal in the system. And F external, if you push your friend on the cliff. All right. Yeah, so F external is if you exert the force on part of the system. Now we understand these two forces. Let's, so if you have like two astronauts, right, in space, and they're like touching. This is called an isolated system, first of all, because it's in space. There is no air drag, there is no gravity, nothing. There's just two astronauts. And they're like pushing on each other. Number A, his name is A and his name is B. Then the F internal, in this case, would be what? Would be the force that this guy applies on that guy. Or the force that this guy applies on that guy. It's the same. That's all internal forces in the system. Nobody touches them from outside.
Yeah.
So that's the F internal. So in this case, we can, do you guys agree that F internal equal FA equal negative FB? Does that make any sense?
That makes sense. But F internal should pretty much just stay zero, shouldn't it? Since nothing different is happening, you know?
Not really. You're not adding them. F internal just describes that there is a force in the system, inside the system. Right? I'm just, this is all lingo, it's just language of physics. You learn the language of science, you start to actually understand what is going on. Because I can't just write F internal and let you figure that out. It's simple. We know from Newton's law that, now we're talking about two things at the same time. Those two things is that, first of all, F internal in the system, it's just the force inside the system. That's the first thing we're talking about. Not rocket science. Well, it's kind of rocket science. But so you guys can get it. It's just a force inside your system. That's all. That's all to it. Don't make it bigger than what it really is. And then the second thing we're talking about is that for every force action there's equal and opposite reaction, all that stuff. So that's the second thing we're talking about, hence this negative sign. Okay? So simply that's F internal, that's the force inside the system. And we don't call this FA, we call FAB and this BA. F of A on B. F of B on A. All of this is just lingo. Just learn the language, that's it. Force of body A applied on B equal to the opposite of these vectors. The opposite of force of body B applied on A. Because they are vectors, we put the negative. So this negative has nothing to do with the magnitude. If this force is 5, this force is also 5. Period. For magnitudes, magnitudes are magnitudes. But then, because they're vectors, we have to specify the direction. And for simplicity, we're using one-dimensional motion. Right? Okay. Now, what is F of A on B? What do you call it? In other words, do you agree that it's a time derivative of the momentum of Mr. A, this guy?
Yeah, it would have to be.
And this one is just the time derivative of the momentum of B.
Yeah.
Clear. Alright, again, what's F external?
The forces that are.
Yeah, tell me. Yeah, exactly. If you go to space and just push them outside of the solar system, F external, what is it? Well, you're not there, so it's 0. Make sense? When you go there, tell me and I will change that to 0. But so far, I don't see you up here. So the external force is 0. So we can just say that the force is just internal in this certain example. Hence, the full force in the system, like the force in this system now, the net force, is 0, right?
Yeah.
Because inside the system, we know that F of AB plus, we just add the forces. When we add the forces inside the system, they add up to 0, which makes sense. Now, can we just do some math, quick? right? What if we add these two together? We're adding them.
You
right?
should get zero.
We're adding FAB plus FBA.
Well, you should have to get zero, I think.
Yeah, but we just want to change the shape of the equation. So can we just like take this d by dt outside of the equation? Tell me if I'm moving too quick in the math here. Alright. Make sense?
I think so.
That looks weird, or anybody has a question, please ask immediately.
No, that makes sense.
Yeah, it's just d by dt of PA minus d by dt of PB. So what you do is you just pull the derivative out and put the things inside. It's called commutative property of derivative. Alright, so, sorry, this is a positive because we're adding them. Of course, we know that this one is negative with that one. That equals what? Can you say that this is just time derivative of momentum? Of course, f equal time derivative of momentum. We're just kind of going in loops, and when you go in a loop, you discover things inside of it. We all know this. We started with this in lecture. We're just kind of trying to see what it means by examples. Like here's an example. In a system, the forces, if you add all of them, you end up with the knowledge that the force is just the time derivative of the momentum of the system. What if the force is zero? What would the momentum be? Tell me, what would the momentum
We
be?
don't know momentum would be, but the derivative of momentum would be consistent with
I
zero.
wouldn't have enough information, right?
Yeah, but if your force is zero, then your momentum is just a constant number, right? Remember, d by dt of 5 equals 0. d by dt of p, a constant, equal f 0. Make sense? Alright. That's all to this part pretty much. The conservation of momentum. We're talking that if you have a momentum in a system, it's conserved. It does not just evaporate, it does not leave the system. Your momentum is always in the system. And you can even see it in the math here. After all this fiddling around, pushing each other, A and B, and forces on each other, you end up that the system has just same momentum the whole time. Make sense? Alright. You guys ready to raise?
You don't even have to equal that.
Alright, let's talk now about, we talked about the conservation of momentum, right? What if we apply collisions of that? The same thing I was talking about shooting people with marbles. So, oh, no. It's conservation of momentum and collisions, right?
Chapter 8, shooting.
Let's talk about this. This is the fun stuff with this chapter. I'm glad we got here. Alright, what kind of collisions would we have? There's 3 types of collision. Right?
Elastic.
Elastic,
Whatever is not elastic.
Inelastic.
inelastic,
Semi-elastic? I don't know.
totally elastic. As a valley girl would say. Completely elastic.
Oh, okay.
Alright. So we have 3 types of collisions. Let's talk about them. Just kind of get an idea of what this stuff means. This gibberish. But once we understand what it means physically, then we can now say, oh, it's an elastic collision. Yeah, I know what that is. Right. In an elastic collision, just i.e. 2 marbles collide. You have 2 marbles and you collide them and they bounce back. That's it. Of course, no collision in the universe is elastic. It's impossible because it can be, some energy gets lost in heat. If you're moving a marble, there's some heat, there's friction, so there's some heat, but very unnoticeable, very tiny heat. A very tiny amount of heat leaves the system. Tiny amount. Heat just means energy, different words. Potential, kinetic, heat, all that coils up the word energy. And we know that energy equals gamma mc squared. The popular equation is wrong, it's for media, this is the right one. Anyway, this is called the relativistic factor, and this is just a scalar. It scales things up, right? It's a big number. You multiply anything by it, it's bigger.
Is that where scalar comes from?
But yeah, it scales things up. We know that energy equals mass, pretty much. Energy is just mass. Pretty much, yeah, that's it. And energy has different words: heat, kinetic, potential, all these names at the end of it, just energy. All right, back to what we were doing. We're talking about elastic collision. Let's jump up a level, okay? Instead of talking about momentum, we talk about energy, right? Here's a law. You write it and you get it tattooed. I don't know what you're gonna do with it, but it's a very important law. Summation of kinetic energy before collision equals summation of kinetic energy after. This is a big K. Collision. All right.
Okay. And this is inelastic collision?
And the elastic, yeah, it's elastic collision. All right, that's simple. If the collision is elastic, no energy is lost. Whatever you go in with, you come out with the same thing. Okay. All right. What's an inelastic collision? That's like if you have a steak and you drop it on your dish. Or your plate.
Is lost.
So this pen, this is
There we
an
go.
inelastic
I thought
collision.
we were doing a whole session without traffic harder.
Yeah. Inelastic collision is when you collide two things together, but something gets lost, some energy gets lost, right? Again, energy is conserved. It gets lost, it does not disappear, it just goes somewhere else. It's not part of the collision anymore. So we demonstrate that mathematically as the summation of the kinetic before equals summation of the kinetic after
Plus some lost energy.
plus a little bit of something, right? We don't have to worry about it, we just need to know. We're just learning it. We're not solving problems. All right, what is a completely inelastic?
Completely inelastic or?
Yes, sorry.
Oh.
What is a completely inelastic collision?
All kinetic energy is lost and it's just some. And so.
You ever took a 50 cal to the chest before?
I have not actually. You can tell by the fact that I'm so.
You ever seen somebody take a 50 cal to the chest?
No, I'm trying to say something.
It flies, right? That's a completely inelastic collision. That's a perfect example.
So there's no bounce.
Not only that, both of them move in one direction. It's like a car crash, but one car is moving really fast and the other is slow. When they crash,
Semi in a small car,
Oh.
it just takes it with
when
it.
they crash, they become one body and they start moving together with a certain velocity. And we can describe that as, yeah. Yeah. So let's say two bodies hit each other. Mass A, right?
At this point in time, you just say.
Let's talk about their momentum though. Okay? Due to the conservation of momentum means for the first body, its mass and its velocity. Actually, yeah. Its mass and its velocity.
Calculate the end velocity of a completely inelastic.
Plus
collision
the
by
second
just,
bodies as well.
Adding the momentum vectors.
What would that equal? Just one body, mass total, right? Multiplied by final velocity, right? Make sense? Of course, this velocity of the body B, It's before. Before.
And then you just add the G.
And this is the velocity we can just go with after. Okay? Just for language, this is not very linguistically correct. So to make it correct, we're moving on the x direction now, just one dimension. We're not talking about analyzing forces and all that stuff. Simple. So we just put an I hat here. You guys ever seen that before?
Yes. Then you start up with component vectors.
Anybody seen it?
Yes.
Yeah.
It's on the.
It's just to say that you're moving in a certain direction. So we're not ambiguous. Anyway.
The unit vector in the x direction.
Yes, that's.
Yeah. It is not a quantity, it's just a
8
direction.
and 13 of our last test. I think.
All right. Now you guys can solve a problem if I tell you somebody took a 50 cal to the chest and then he jumped and he moved, like he jumped really fast. How fast was he moving?
You got shot out of the air.
This, we want to find this. This is when you take that
No, we
bullet
can
and
just
just
leave
jump,
50
how fast are you moving, right? So in total would be your mass
Realistically,
plus
we just go through the
plus the bullet's mass, right? Make sense?
Do you want
This would
the-
be your mass. Your mass.
Yeah.
Do you want the velocity of all the pieces?
Yeah. We're doing this in a thank you for mentioning that. We're doing this in a perfect world. Where when the man takes a 50 cal to the chest, he does not disintegrate. So you still took it, and you're still one system, one piece, all of you with the bullet. The whole system is just one. And it moves with a certain velocity, alright? I can disintegrate it and you'll have to do the math. Do you want to do that?
Yeah.
Or you want to do it simply? Simple or else stay simple. So this is the mass of the bullet, right? That's the speed of the bullet. That's your mass and your speed. If you're moving, you can put your speed. If you're not moving, because you think you can dodge it. So this would be zero, all this quantity, right?
Yeah.
And if I tell you the mass of the bullet and the speed of the bullet and your mass, only by these three things, you can actually get the velocity after. Isn't that cool? There's definitely a question like that in your exam.
I watched that show. Do you think you can dodge it?
All right. What else are we talking about? What about kinetic energy?
It's conservative, George.
Yeah, exactly. Since momentum is conservative, then kinetic energy is also conservative. What about it? What happens before and after?
It should be the same. No, it shouldn't be. Because even the masses of the velocity will change significantly, and kinetic energy is not proportional to velocity.
Yeah. Can you say that kinetic energy before?
I think it should be less than. I mean, it should be more than
Bigger.
kinetic.
Kinetic
Yeah,
energy after.
I think so.
That's correct. All right.
Wait, so where does the energy go?
What?
Where does the energy go?
In the air, heat, friction. Yeah, mostly. So it's something, but kinetic energy before means your kinetic energy plus the bullet's kinetic energy.
Yes.
Right? Your kinetic energy is zero because you're standing still. Right? And the bullets,
Has some.
yeah, huge kinetic energy. Even after it hits you, now the kinetic energy is half and total V final squared, right? Now this is your mass plus the bullet's mass multiplied by the velocity squared final. And all of this velocity is not going to be fast enough, as fast as the bullet. The bullet is going like, what, 80 miles an hour, 100 miles an hour?
I would.
But then when it hits you, you're just moving like, what, 1 mile an hour? 2 miles an hour, let's say. So that was going to be 4. Your mass, let's say your mass is 100 pounds, and the bullet is a pound. So, or 99 pounds, and the bullet is a pound, so you end up with 100. All right? But here, the speed of the bullet is really fast. It's already 100. and then, of course, it's half mv squared, so 100 squared multiplied by the mass of the bullet, which is 1 pound. You end up with what?
5,000 joules.
Yeah,
Joules.
exactly, 5,000 joules.
Not something, but.
And that's definitely bigger than 200, right? Makes sense? All right. Part 4. We're almost getting to the good stuff. Bear with
We're
us.
cruising.
Anyone else take a picture?
No,
Good.
there's just. You do this with your Russian accent, but you.
Yeah.
I do have a quick question.
Yep, go for it.
I know we talked a lot about like energy being dissipated in like heat and a couple other things, but isn't sound another one of those where energy is dissipated? I don't feel like it's talked about a lot, so is it like super negligible, but it's just not very popular?
It is not super negligible. It's just, it's a wave. And that wave, what is a wave? It's friction between molecules of air, so it's,
Okay.
it ends up to be some sort of heat.
Oh, okay.
Okay. All right, good question. Thank you. Now, let's talk about elastic collision. Now we understand what elastic collision is, what's an inelastic collision is. That's the pen on the table. And what's a completely inelastic collision. All right, so let's talk about elastic collision a little bit more broader. We said that K before equals K after, right? Kinetic energy. Again, what is kinetic energy? Right, we know that. Of course, this V is a scalar. With this also, this assumption tells us that the momentum before equals momentum after, i.e. two marbles hitting each other, two billiard balls bouncing from each other on a table, right? If you just bounce two marbles off each other, the what is it? The momentum before equals the momentum after. In other words, what is momentum for two systems, right? MA, VA, right? Plus MB, VB. Of course, this is before, right? What would this equal to? MA, VA after, plus MB, VE after. Of course, these V's are not the same. You have 4 different velocities right now. Okay? A big marble and a small marble. This is going really fast. It's going really slow. They hit each other. Sorry, this is fast. So the vector is big, faster. And this is a little bit slower. Because the size is big and the size is small. When we hit and bounce, what happens is this one will bounce with a bigger velocity, and this one will bounce with a smaller velocity. So the velocity kind of moves around. But you can't tell that this one is this one now and this one is this one. You can't tell, you can't say that. Right? But definitely you have different types of velocities right now. In a problem like that, you will get the first two. You'll get the masses. The masses are still the same because it's an elastic collision. The mass doesn't change in this case, right? But the velocities change, and you just have to figure out this velocity and this velocity. That's the kind of problems you get.
And how do you figure out those velocities?
Yeah, this will end up a number, and you will have 2 equations, and you solve them together, and you will find the velocities. Okay. Tell me if what I'm going to do now makes any sense. Yeah? What?
Just rearrange the
Exactly.
equation right.
This is a very magical formula. Keep it in mind.
I have a question.
Yep.
Okay, so we said that like momentum is gonna like conserve, right? Is just the magnitude of momentum conserved, or is the direction of momentum also conserved?
It's a good question. Direction is a direction, right? You're going deeper now in the essence of the universe. Direction is called a translation or symmetry. Remember I was talking about that?
Yeah.
So that is something else. Momentum is conserved now for just for the magnitude. The direction is also conserved, but on a quantum level. Right? Good question. All right. So you guys studied relative velocity before,
Yeah.
right? So if we use this and ignore the masses, can we say that VA before minus VB after? Can you tell me what happens now? Sorry, VB before. Eventually, you'll find out that this is equal to negative VA after minus VB after. Of course, all of this is one-dimensional. All of this is happening along the x-axis. We haven't even touched what would happen if this is two-dimensional. We're just using the simplest version of it, so there's always an I hat hanging around, you know? With every vector, there's an I hat. I don't want to confuse you, so I'm doing the simplest shape possible without writing, like in the book, this is written like V A to X, and you just gotta figure that out. So yeah, that's a little confusing. This is how the book read it, okay? But just V is the velocity, and it's a vector, right? That's why it's written in italic font. And A is body A, there's two bodies, A and B. 2 is before, after, so that would be 1. Yeah. 1 is before, okay? And X is just the I hat I'm talking about. That this velocity is going on the X axis. But just, I don't like how this looks like. Do you guys agree or disagree? Yeah. Yeah, but just so you know, when you read the book, which you really should do, this is what this is.
So if it was a multi-direction, it would just be the velocities to each direction you figure out.
It blows up, man. It just blows up. So let's just keep it.
Just don't worry about it.
Keep life simple. This is all one-dimensional. All right, on the x-axis. All right, and that's all to it. All there is to it. Now you know everything about elastic and inelastic collision. When I say it, do you understand what these forms mean?
Yes.
If you have an elastic collision, what is that? It's two marbles and a billiard table. What's an inelastic collision? It is if those marbles were just made of a squishy material, and when they collide, it's not elastic anymore because they stay colliding for a little bit.
Yeah.
And then completely inelastic.
50 cal for the chest.
Yeah, 50 cal for the chest. But you're not gonna disintegrate. Keep that in mind. You're German. Anyway. You guys ready for me to do this?
Yes.
All right. .com. What is this? This is center of mass.
Oh, okay. It was like that count.
Center of mass. Let's talk about something like, I wish I had a wrench. What?
Yeah, you can dodge wrench, you can dodge wrench.
Yeah. A wrench, so if you move it around, see what's happening? Just imagine, you can't see it, just imagine. It's spinning, right? That's not spinning. It is moving in a straight line. The center of mass moves in a straight line, always. You guys have the book?
PDF
If you have a wrench, right? This is a wrench. It's heavy up here, and it's not very heavy down there. The center of mass is represented by the black point. When you move it on a table, this point is always going to be moving in a straight line. The wrench can dance around. That's pretty much the motion of a center of mass.
You want that picture?
What? Yeah, you have it there?
Yeah.
Yeah, so.
Oh,
This is it.
way too much for me.
See this picture? That's a wrench, and you just push it on the table. It's gonna spin around. The spinning is actually what the Fourier series. But anyway, just a random spin. But the center of mass is the white dot, and it's always in a straight line. That's pretty much what center of mass is. If for a marble, center of mass is exactly in the middle. Very simple. You push it, it goes in a straight line. But for a non-marble object, what would happen? And that's what we're going to talk about now. The mass collects itself to a point, geometric point in the object. And that point is called the center of mass. So now you can view the whole object, whatever shape it is, in just a point. Isn't that cool? That's a very, very fundamental, very good concept if you think about it. Makes life easier. If you have a wrench and you want to analyze its motion, it's just like impossible, dude. But if you consider it a marble, yeah, this is pretty much what we did. The concept of center of mass takes a wrench and makes it a marble. And now you can deal with it. You know, you can study it, you can move it. You can really know how to hit your friend in the face.
So thinking about that,
Yeah.
say you throw the wrench, that means that center of mass, I guess, would you say, is that what's gonna be like a consistent parabolic shape as it comes down?
Exactly. Because of gravity, of course. But in physics, we always ignore air drag, ignore gravity, these things, to make things simple. That's why we move it on a table on the x-axis, so we can try to avoid gravity just going around it. But if you throw it in 2 dimensions, it's going to go parabolically. But a parabola is just a one-dimensional line, right? It's a parabola in 2D. That is just a line in 1D. It's just a line. But we're trying to ignore gravity. Thank you for the question. All right, let's talk about center of mass. Let's talk about the math behind it, okay? We're using the conservation of momentum right now. So particle with mass, let's talk about a bunch of particles, okay? Those particles have masses, mass 1, mass 2, you get the idea. But those particles are also moving, right? Not moving, sorry, they're stationary in different positions in a 2-dimensional plane. So this particle, what would be the coordinates for it? x1, y1, makes sense?
Yeah, okay, that's a very good.
And then x2, y2,
Etc.
yeah. So we know the particles and we know the positions in space. Now can we describe the position of the center of mass of all these particles? Like this wrench. It's made of particles, right? Like it or not, it's made of particles. They have bonds, but plenty of particles in different places in space. If we know the mass of each single particle, and we know the position of each single particle, we can map it. We know where it is, like 100% right now. We know exactly where it is. Let's reduce all of this to just one concept, where we only have one mass, the center of the mass. only have one position. The x, center of mass, and the y, center of mass. That's what we're looking for right now. That's what we're hoping to get. And the equation for this is pretty straightforward.
Sum of x times mass, then.
Yeah, so the position on the x-axis of the center of mass equals, you get the idea.
Yeah.
And what about the masses? M1 plus M2 plus blah, blah, blah. Okay, is that clear?
The x position.
What about the y position for the center of mass?
Exact same thing. Your
Same thing.
Position scales to the mass.
Do you guys understand the fundamental achievement we got to right now? Is that if you have a wrench, you can actually figure out its center of mass. Given that you know all the data about the particles that make it up. But think about this in another way. If you have a spaceship that's weightless, okay, that spaceship, just hypothetical, okay, that spaceship has no weight whatsoever. It's just a geometry, it's just a 3D model. And then you put objects in it that have masses.
Yeah.
You put people in there, and those people have, each person has their own mass, right? And these people have positions as well. They're not all in the same place. They're moving, they're in different positions and they're not moving around, standing stationary. So imagine that in your head. You have a spaceship. It doesn't have a mass, okay? I know that's illogical. What are you talking about? But just for the sake of argument, the spaceship has no mass whatsoever, made of frame photons. And you put people in there, right, in different positions. Each person has a mass, and each person has a position. If we know that data, we can map the center of mass. All right? Great. And this is how we map it. Pretty straightforward. You can write this in a different way, like this, just a summation of mi, xi. And if I is any number, you just add all of them together, just laying them. All right, so are you telling me that generally, x and y is just coordinates for a point? But if the point is not in the xy coordinate, any other coordinate, we can describe it with position vectors, right? So that's a general shape of it. These x and y, you know, like these x, center of mass, and y, center of mass. Instead of writing it this way, which is a very special case, we can write it in this way, which is easier and more straightforward. Right? And that equals what? Luckily, that is pretty straightforward too. Over, what is this? Yeah, it's just adding all the masses. Can we just write it in total? Okay. Alright. So center of mass moves in a straight line and the body dances around it. That is all there is to it. If you have a body that's moving chaotically, you know that's not chaos actually. There is order beneath that chaos, and the order lies in the motion of the center of mass. The body has no center, has a center of mass, so it does some chaotic movement. But underneath that, the center of mass is actually not chaotic at all. It's just moving like a marble. That's pretty cool. So, or maybe I'm a nerd. I don't know. Let's talk about velocity now. Okay. Can we just use this x and make it v? If we get the time derivative of this position, it becomes velocity, right? So we'll have velocity of center of mass in what? The x direction, because the x, right? And velocity of center of mass in the y direction, which is g. And that would equal what? Similar to that, just mass times velocity. course, this velocity is here, you know, all of this is in the x direction. And then you write the same thing down here, but in the y direction. Can we write it in a more general form? Write these two in a general form. Just like we wrote these two in a general form. We can write these two also in general form. And that general form would be V of center of mass. Alright? Equals M1 V1 plus over M total. Okay? That's quite clear. So, just look at this for a minute. I want you all to look at that. Alright. Do you understand where this came from? Let's take a break for 5 minutes. Is that okay?
Is it class over?
Class is over in like 15 minutes.
I don't know if he's gonna keep lecturing.
Technically can't because I don't have to take the lab. You could do it. That's true.
Let me learn those. I'm not submitting. Did you really get into the questions? What's next week?
Huh?
Why don't we have the class next week?
Why not?
Oh, is it? Oh, okay, sure.
I think we'll have class next week.
Yeah, so we'll have it next week, so we'll
Always need one.
When did we get our tests?
What?
Yeah.
He said that he was hoping to have him back.
So you graded our test yet? It's taking a while.
Anyone get 100% thus far?
You don't wanna know?
I mean, I kind of really did.
If it's up to me, I would give 100%. This is what I would do. I would grade you on the test harshly. Hear me out. And then give you the test back, and then you do it again, give it to me, do it again until you get done. So you're learning, yeah? You just have to work hard. You're here to explore your passions, pretty much. You have a passion. You like something, even if you don't know. You like something, and you just gotta figure it out.
Yeah.
Once you figure out what you like, work hard. Because there's no smart people. There's just people who like something and they really work hard. That's it. You work hard, and you just gotta learn to work hard and be stressed and hate yourself for a little bit. And then you're a functioning member of society. Okay, ready? Look at this part. What do we got here? Do we understand where we got this from so far? We got the center of mass. We know that the center of mass is described by the position and the mass of the small particles in a body. And then we can describe it and then generalize it as a vector of position. And then when we find the derivative of this vector, that ends up to be velocity. That's all we did. We just found the derivative of the position, the time, with respect to time, and we end up with the velocity of the center of mass. Alright, let's not milk that part. What would that mean? What if we move this in? What happens?
We divide that total.
Yeah. we're
I mean, if we
going-
multiply by that.
the total mass multiplied by the center of mass Y'all with me here? M1, K1 plus M2.
Can you do an example of this really quick? Can like
This is why I study
simple
physics.
system?
All of this computation that's logical, and we reached to it and agreed on it, we end up knowing that momentum is conserved. Momentum of every, you remember momentum? P equal what? Momentum of the whole system, but our velocity is the center of mass velocity, isn't that cool? Because of the whole system, how do you find the velocity of the whole system? That imaginary spaceship with the people standing in different positions, how do you know that the velocity collectively is the velocity of the center of mass? You know how to find that velocity, it's pretty easy, pretty straightforward. Multiplied by the total mass of the system, so the velocity of the center of mass, multiplied by the total velocity, that is just equivalent to the small momentums of all the particles that make the system. There you go. That is the relation between momentum and center of mass. Now let's talk about this system with an external force. Okay. If you apply a force in that system, means the momentum is not conserved anymore, because you added something to it. And also, this velocity is not going to be constant anymore. Think of it. You have a system and you apply a force to it, the velocity is going to change. That simple, right? When you change velocity, what happens? You get acceleration. So, if we find the derivative of this, what would it be?
The derivative of the momentum.
Yeah, this. That's what I'm
As
saying.
force.
Mathematically, I can say, find the derivative of this. Physically, I can say, apply a force on the system to change the velocity. Same thing, I say the same thing in two different languages. The language of math and the language of physics. Language of math, find the derivative of that. The language of physics, okay, apply a force on this system, and when that force is applied, it changes the velocity, the center of mass velocity, and when you have a changing velocity, then you have acceleration, right? Which is, find the derivative of this. Mathematics is very word efficient. So, all right. What we have now is, we just find the derivative. So we end up with m total acceleration of the center of mass. What would this equal to? Pretty clear, no? And now you can just write it in a different way, which is just the summation of forces. Okay. We know every system has external forces and internal forces. We agreed on that. Are there any internal forces in this system?
I mean, yeah, there would be. Because
Think of it this way. All the masses in the system, M1 plus M2 plus M3, all these masses, they become one mass, the center of mass, right? Which means any internal forces in there, it's just, they all cancel out. So you end up with just the external forces, and from that you get this beautiful equation that the external force equals, what is this? That's MA. Can you call that the derivative of the momentum of the system?
yeah,
Because F equal MA equals dP by dt. Remember that? Newton's second law. We just proved it. Alright. the last part of this chapter, and it's not really that hard. It's pretty intuitive. Rocket propulsion. All right. So far, we described systems where F equals ma. Right? We're finding derivatives, we're playing around with it. M is always constant. M is not changing, always. Right? What if you're in a system where M is changing? Like a rocket. A rocket is launching. The rocket is coming off the ground. The fuel is burning and leaving. So your mass is getting lighter.
Force equals the integral of mass, though.
Yeah, something like that. So let's describe that, all right? If your n is changing, then the summation of the forces is not equal to ma anymore. The force of the system is not ma anymore. It doesn't make sense because your m is changing. All right, let's say you're going to start your motion. The rocket is going to launch. The momentum would be what? mv, simple. The mass of the whole rocket multiplied by the velocity at the beginning. All right, which is a very, very tiny velocity. Okay, do you agree that the velocity of your fuel equals the velocity of the rocket plus the velocity of the exhaust? Think of it this way. The total velocity is how fast your rocket is going, plus how fast the fire is going as well.
Yeah.
But because the fire is going in the opposite direction, you put a negative. And that gives you the velocity of the fuel.
Yeah.
Alright. Let's and because your mass is changing, we know that the mass is changing now. We know the mass is changing of the whole system. So how is it changing? It's changing by a factor of dm. Does that make sense? A little bit of mass is coming out every now and then. That's why the d, the derivative. D just kind of means delta, means m2 minus m1. So, but just smaller than that. Because you're losing mass while ascending up. So if we multiply dm by both sides of the equation. Now let's play with this part. Do we all agree on this? That this makes sense?
That's right.
All right. Well, what do we do now? You can just multiply it around. We all know that momentum is conserved. We have mass and we have velocity. That's momentum. We're talking momentum right now. So can we say that momentum P2 after launching equals mass is dm multiplied by velocity is dv. I'm going to clarify all of this. Alright, what do we have here? You see this part? That's just that part. I'm sorry, I forgot to put a negative here. You know why? Because when you're losing a mass, you're losing it in the opposite direction of the mass that you're using. Again, remember Newton's law?
Yeah. It's all right.
You can just apply that to mass as well. I know mass is a scalar, except in this special case, it could be treated a little bit like a vector. It's not a vector. But the mass you're losing, when you burn it, it's going in an opposite direction of the mass you still have and going up. So you end up with, so that's why the dm is negative, because the rocket is losing some parts of its mass, but it's going down while the rocket is going up.
At the moment, like the total system of the rocket and its exhaust is gonna end up in zero.
Yeah, if you had all the momentums together, it would be definitely zero.
Like the exhaust particles, you would just end up with.
Yep.
Okay. Okay, I think that makes sense. Okay.
Momentum is always conserved, means momentum before,
Because there's no outside force.
Plus-
messing with the system. Okay, yeah.
momentum after equal 0. It's just like saying that momentum before equal momentum after. So he's talking that, what if you add them together? You get a 0. Alright. This came from that, just algebra. Just a little bit of math. This is V fuel, this is dV. So you'll have this one in the book. I don't think you have a lot of time to kind of derive this, but if you see this equation, do we all agree that this is correct?
Yeah. You've got more than 100 seconds, so.
I'm debating if I should guide you through it or just leave it the way it is. All right. So this part comes from this part and this part. Is that clear? dmv fuel, dm v.
And dm is what again?
That's the little bit of mass that burns
Okay, so
when you
you
launch a rocket.
Okay, yeah, okay.
All right. So you end up, when you move this one to the other side, now you have your momentum after launching, after burning some of the fuel. And from this, you can get that mdv equals negative dm v exhaust minus dv. That makes sense? All we did is we just distributed this m on here and on that. So dm v, dm dv, dm v exhaust, dm v exhaust. Simply, your momentum is equal to the momentum you lose. This is the momentum you lose when you start the rocket. When the rocket goes up, it has its own momentum here, but this is the momentum that you push against because it's dv, small increment of the velocity, and that would equal to the small increment of mass that you lose multiplied by the velocity of your exhaust. Well, exhaust is the mass. It's the same thing, it's the fire, right? That's the mass, that's something burning, right? Some mass. And it's moving in that direction down, and you multiply by the velocity, by its own velocity. Because you always multiply a mass by its own velocity. You get momentum. Minus dmdv, which is very tiny, so we cannot just ignore it. Very tiny.
If you're multiplying something that's infinitely small by something that's infinitely small.
Exactly. And then what do you have? Can you differentiate this? What do you get when you differentiate this one? You get force, right? In other words, just put a dt under that. A dt down here. That's it. Now you have mass times acceleration equals what? This is just d by dt of m. You agree? Multiplied by v exhaust, and this is the rocket move. The force of the thrust equals negative velocity of the exhaust multiplied by the temporal derivative of time of mass.
Not the mass that's being out.
And that's the rocket equation.
Awesome. That's a really complicated way of saying something that's not that complicated. But
It
yeah.
is not very complicated. This is telling you that the force, that the thrust pushes the rocket upward, equivalent to the velocity of the exhaust, the velocity of that fire, multiplied by the time derivative of the mass, how much mass you're losing over time. You're losing mass over time and you're burning it, and it's burning with a very fast velocity, and that's just the thrust you get. That make sense? Alright. This is all there is to it. Is to just know that when you use momentum, P equaling V, you do some calculations, you understand that your mass is changing, that's why we multiply this here and here. And when you're losing some mass and your mass is changing, eventually you end up understanding that the velocity of the exhaust multiplied by the amount of mass you're losing over time, the rocket is getting lighter, that's just the force of the thrust, and now you can calculate how much thrust you have. Now, bear with me for a little minute. What if we take the mass out of this force? What do we get? Divide by mass.
The acceleration.
Yeah. If you want to know the acceleration of the rocket, it would be v exhaust over mass dm. Does that make sense? This is a very, very important part. I'll tell you why in just a second.
So would that be like an instantaneous acceleration then, since the mass is decreasing?
Exactly. So you're losing some mass. That's just this. Even this acceleration is changing. We're all used to constant acceleration, but this one keeps changing. And eventually, let's integrate. This looks ready for integration, isn't it?
No, that does.
Yeah. What would happen if you integrate the acceleration? You agree that you just give velocity?
We get rid of velocity.
Yeah. There is a lot of math between this, but I'm just cutting to the chase. What if you integrate this part?
The integration of velocity of the
Well, the integration, the velocity here is a constant, the velocity of the exhaust. So let's just pull it out.
Yeah. So you get the velocity, you get the integral of.
And
one
when you
over
integrate
m.
this 1 over m, you get ln, right? Degenerate. You get the log. You get the log of the final mass over the initial mass. And there's a better way to write this. Look, this negative can switch these. So if we get rid of this negative, then we can just have the initial mass over the final mass, like that. And that's the rocket equation too. That is, if you want to know the velocity of your rocket, if you know the velocity of the exhaust, the fire, you can measure the velocity of the fire coming out of the rocket, and multiply it by the logarithm, the natural logarithm of the mass of the rocket, the initial mass before launching, over the final mass, the current mass, you can get the velocity of your rocket. If you ever do hobby, you launch rockets for hobby, this is exactly the stuff these two equations, just this one and that one, can tell you everything you want to know about your rocket. And just a final note, a rocket launches from the ground. If you're launching your rocket, the fire is pushing against the ground, that's why it's going up, right? Makes
Well,
sense.
at the start.
Yeah, but why does it keep going? There's no ground to push against, like, what is going on?
Pushing against the air.
Well, then,
What about in space?
well, then it's,
Oh.
you're
no
just
idea.
taking advantage of the conservation of momentum because you are, because you have some mass that is.
Exactly, and that's why I did this last part.
Because of conservation.
This part tells us that the rocket is not pushing against anything. It's just momentum. It's losing some momentum, and that momentum is giving it a push up. It's just like that system, the system of the two astronauts. difference in your velocity equal to the v exhaust multiplied by the natural logarithm of the mass. Think about this for a second. This is just velocity and mass. Momentum. This is momentum stuff. We know that momentum is just velocity and mass. Which means this kind of looks like velocity multiplied by mass, right? Well, this one is a ratio, this one is dimensionless. But for the sake of argument, you're talking about momentum here. Delta V over V exhaust equals ln of initial over n final. In other words, e to the v equals what? Initial over n final. So the natural, if you put the velocity to the power v, that's the mass. These are just other ways to see it. But that kind of tells us that the rocket does not have to push against anything. Before, in the 50s, they were like, when the rocket goes to space, it can't push against anything. So how is it going to keep moving when I go to the moon? Because we went to the moon with this chapter. That's all we needed to go to the moon.
It's like,
Physics 1 and Physics 2. That's all they needed to go to the moon. Those two classes. There's 100 more classes after that. Didn't get us to the moon. So all of it is just classical mechanics. All right, we're done.
all right.
This is fun.
Do you teach every class?
Right. No laughing.
Thank you.